Well, my revised title is about logical English, which is inspired by legal language but executable by computer. This is very much work in progress, so you don't yet have a final presentation here today. I hope to come back and give you more inspiring talk in the future. This work, of course, has not been done alone. It's been done with a number of colleagues, and I want to mention them right at the beginning, but also again at the end. Let me start at the end of my talk. In 1993, I wrote a paper called Legislation as Logic Programs, and this paper was widely reported in the press, including the Times newspaper. And in one of the press reports of my paper, it was said that the future of computing lies not with programmers, but with lawyers. Unfortunately, this did not make me very good friends with my computer science colleagues, nor with the mathematicians who share the same building with us. But I want to return to that idea, which I argued about how many years ago? 25 years ago, because I think we've made some progress to prove my point during that time. So what is logical English? Of course, it could be logical German, it could be logical Polish. But in any case, it's modeled on the language of law, but it can be executed by a computer. It can be understood by English speakers without any training in computing, indeed without any training in logic. It can just be understood by understanding natural language alone. I believe that one day it'll be suitable for general purpose computation, replacing the programming languages that we have today, replacing the database languages that we have today, and knowledge representation languages that are being used in artificial intelligence. We have several prototypes in the programming language Prolog, but there's still some way to go. Let's compare the language of law, which is the inspiration for logical English, with the majority of computer languages that we have today. First of all, law is declarative. You can talk about whether a sentence is true or false, but the majority of programming languages are imperative. They issue commands to a computer, telling a computer what it should do. And typically what the computer should do is change what is inside the memory locations of the computer. In order to program in the majority of computer languages today, you have to think like a computer. In the language of law, we describe the legal consequences of actions and events. If a party performs an action, then the law or a legal document, whether it's a contract or a piece of legislation, tells us what the legal consequences are of those events, how the state of the world changes in response to changes in the world. But in the majority of computer languages, we control memory locations in a computer. This has nothing to do with the way humans think. And in order to program in the majority of computer languages, you have to think like a computer. In the language of law, we use logical expressions. We use expressions which are logical conditions. If certain conditions hold, then certain conclusions will hold as a consequence. We talk about all parties to a contract. We talk about all people who are born in the United Kingdom and whether or not they will be citizens of the United Kingdom. So we have logical expressions in the language of law. But in computer languages, we have if-then-else statements. If-then-else statements which are not found in the language of law or in ordinary natural languages. We have iterations and we have loops. Yes, you can learn to code, you can learn to think like a computer, but why do that if computers can be made to think like us? In the language of law, we attempt to avoid ambiguity. We attempt to express ourselves in a meaningful way, which means the same thing for you as it does for me. We allow vagueness or open texture so that we can be flexible about the definition of terms which might not be well understood, which might vary from time to time and from context to context. But of course, computer languages are unambiguous by design. And indeed, there's nothing wrong with, indeed, it is highly desirable that computers be programmed in an unambiguous fashion. But one of the reasons why the language of law is declaratively is because it passes passive judgment on states of affairs and behavior of agents. The law is not an actor. The law is a judge that passes judgment on the behavior of external agents. On the other hand, computer languages are active agents. They act on behalf of clients, stakeholders, but it's the result of acting on behalf of them. They perform actions, which is not the case in the language of law, and they also are given commands, which is why these languages are typically imperative. Now, the two worlds, the world of the language of law and the world of computer languages, come together in the area of smart contracts executed on blockchains. So this application area is a kind of killer application for any language which is designed to be based on the law. And what do we find with smart contracts? That they, unlike the language of law, actively support the goals of the stakeholders to legal agreements, and therefore they do perform actions. They transfer funds. They may send notifications of transfer of funds. They may send warnings and other notices. So the field of smart contracts gives us an opportunity to see how the two worlds of law and computing come together. In my talk, I will illustrate logical English with 4 examples. The first example historically is interesting and indeed important because it was done, I think, about 35 years ago, and it had a major impact at the time. The second example is quite a recent example. Let me first make a little bit more detail. So the first example of the British Nationality Act showed how logic programs are close to the language of well-written legislation. The second example, a very recently investigated example, has been used by legal scholars in order to argue that deterministic finite automata from the world of computing are a better way to think about legal contracts than either logic or the language of law. And I want to disagree. So I will look at the example and show you how we can do better than deterministic finite automata by expressing the simplified loan agreement in logical English. The third example comes from lessons in a cryptocurrency lab at the University of Maryland, and it's a good example of a smart contract which actively transfers funds in a game, transferring funds either to the winner of a game or distributing them back to the original players if there's a draw. Because it's active, it's written in an imperative language, the language Serpent, which is a variant of Python, and it's a conventional computer language. I want to investigate to what extent the use of imperatives is important in that application, and what does it mean for logical English? Do imperatives have a logic? And if so, what is that logic? And finally, the last example that we've been looking at over the summer is the International Swaps and Derivatives Association Master Agreement. And there we have a case of very complex obligations, with one obligation overriding another obligation, replacing it in certain circumstances. And again, I'll want to look, in this case, how logical English can represent complex obligations. Well, to go back then, or to the beginning of much of our work at least, in logical English, let me show you the first clause of the British Nationality Act written in the original English. So in the original English, we have a sentence which says that a person born in the United Kingdom after commencement, that is to say the date on which the Act takes effect, shall be a British citizen if at the time of the birth his or her father or mother is a British citizen or settled in the United Kingdom. Now, is this English or is it logic? And to what extent does it deviate from conventional, more symbolic or more traditional logic? Well, it deviates primarily in this phrase, born in the United Kingdom, because although the sentence has conclusion if conditions form, the conclusion has embedded inside of it two conditions. So when we rewrite this in a more logical, more transparent manner, we separate out the conclusion, namely that a person acquires British citizenship, and are more precise and say, in fact, that they acquire their citizenship by means of this particular section, because a person can be a British citizen according to other sections of the Act, for example, through naturalization or through registration. And if you acquire your citizenship by some other means, you may not have the same quality of citizenship as you would have if you acquired it in this manner. So in logical English, we clearly separate out conclusions from conditions. Embedded in the original English was the condition that the person is born in the United Kingdom at a particular time, and that time is after commencement. And of course, we have the other conditions, which are logically at the same level. There's no logical distinction between where you are born, when you are born, and who your parents are. So the other conditions are that there be another person who is either the father or the mother of the person, and that the other person be a British citizen at the same time or be settled in the United Kingdom at that same time. Now, this is a rather stultified form of English, so let me go back to the original claim. Oops, it's taking a bit of a while. I've probably made a mistake in doing this. So, read what's inside this red circle. We don't claim that logical English is the most natural English, but we do claim it can be read. It can be read and it can be understood by human beings, and it can also be read and understood by computers. Now notice also, one of the ways in which we represent the logic is we have logical variables. These are not the same as variables in the imperative computer language sense. They're not values that change over time. So a variable in an imperative programming language is some location inside the computer whose contents changes over time. But a logical variable is a term which can be instantiated in various different ways. So a person can be you, it can be me, it could be John, it could be Mary. And the first time we refer to this variable, we represent that variable by the indefinite determiner a, an, or another. So here you see, oops, I knew it. So this is the first occurrence of the variable. This is the second occurrence, fourth and fifth occurrence. It's the same variable, x, called it x. And then, so the first occurrence is prefixed by the indefinite article. It's indefinite, which individual you're talking about. And then the later occurrences are prefixed by the definite article because it is definitely the case you know who that individual is. These variables, these logical variables, are typed. So there is an X of type person, and that person acquires British citizenship under certain conditions. Notice that this logical English is not like Aristotle's logical syllogisms. There are no all, every, or some. And that's because it's simpler to just say and the. So let's look, for example, at a typical sentence that might be logical, of course, but nonetheless use terms which are more familiarly logical. All payments that are specified in some transaction are obligatory. Here you have all, here you have some. These occur in ordinary language, they occur in ordinary logic, but they are unnecessary. It is possible to replace them by a and the. Moreover, this phrase that are specified is a conclusion rather than it is part of the conditions rather than the conclusions. So what we would do is rewrite this. For example, and this is only one way we could write this, we would rewrite this by saying a payment. This is a logical variable. First time that it's referred to, it's an indefinite common noun. A payment is obligatory if the payment, second time we refer to it, is specified in a transaction. You could replace these by x's and y's. X is obligatory if x is specified in a y, and x is a payment and y is a transaction, because these are type variables. So we can take this form of English and transform it into a lower layer, which is very close to the prologue layer, as it turns out in our prototypes. But that's not the only way we could represent this sentence. So although we have a language called, or are working towards a language of logical English, we also need to work towards a style of writing in this logical English language. And there's another way of writing the same sentence with the same meaning. We could say it is an obligation that a payment is made if the payment is specified in a transaction. And this particular way of representing that sentence, instead of being obligatory as a predicate, having obligation as a type of entity, gives us far more expressive power and allows us to talk about obligations. It allows us to say that one obligation might override another obligation. It allows us to say what are the conditions under which an obligation might be satisfied. When is an obligation breached? None of this is so easy if we adopt the first style. If we simply say that a payment is obligatory, it makes it harder to say that this obligation has been breached or that the obligation has been satisfied. So we have the beginnings of a language called logical English, but we are still struggling somewhat with the style which is most appropriate for representing knowledge in that language. Ideally, and hopefully, this language is expressive enough not only for representing the information in legal documents, but also for more general information that we might want to use to describe the world in which we live. So that was my first example. Let me see how we do for time. My second example is, in a sense, a counterexample, or so the authors of this paper might argue. The second author, Oliver Goodenough in particular, is a legal scholar who says English is not that great for thinking about law. English is not that useful for understanding law. And a much more useful way of thinking about law is to use the notions of deterministic finite automata that come from the world of computer science. And he and his co-author look at this rather nice simplified loan agreement, which talks about a loan being given from a lender to a borrower, and the borrower needing to repay the loan in 2 installments over the course of 2 years. And much of the loan is taken up with not so much describing the green path where everything goes as planned and goes as hoped for, but most of the loan agreement is taken up with describing what happens when things go wrong. What happens, for example, if the borrower does not pay those installments, and how long does the borrower have to remedy or cure the default that would arise if that payment is not made, and then what happens if the cure does not take place. The authors show a finite automata, and this is what it looks like. It's a pretty picture. It looks like a flow chart of sorts, and it certainly makes it puts a smile on a computer scientist's face because it makes them feel indispensable. So let's look in detail at a very simple sentence. This simple sentence corresponds to this path where the lender does or does not advance. The first part is where the borrower asks for right up here. The borrower, is that right? Can you read this? No. The borrower requests the loan, that's the first path. And if the borrower does not does not request the loan, then everything is terminated. And then the next question is whether the lender advances the loan. If the lender advances the loan, then everything is on the green path and going according to plan. But suppose the lender does not advance the loan. So let's look what the English says. The first sentence, number 1, says, at the request of the borrower to be given on the 1st of June 2014, you can see when this paper was written, therefore, the lender will advance $1,000 to the borrower no later than the 2nd of June. If the borrower does not make such a request, this agreement will terminate. So the authors of this paper claim that this English is not very helpful. They claim if you want to automate the law, if you want to have legal informatics, it's better to translate into deterministic finite automata. And notice, by the way, these two English words, will. The lender will advance the $1,000. The agreement will terminate. Now, the English language uses this word will twice, but does it use them in the same sense? Does it use them in the same sense? No, it does not use them in the same sense. The first will represents an obligation of the lender, and if the lender does not advance the $1,000, then the lender is in trouble. On the other hand, if this agreement will not terminate, then nobody gets, there's no avoiding the agreement term. It will do nothing else. There's only one way forward. So this is more of an action. This is that takes place terminating the contract. So let's look at a representation in logical, executable English. It is an obligation. I'm looking now at the first sentence. It is an obligation that the lender advances $1,000 to the borrower at a time, and the time is before the end of the 2nd of June 2014, if the borrower has requested that $1,000 on the previous day, the 1st of June 2014. So the first sentence represents an obligation, whereas the second sentence does not. On the other hand, the first sentence can be written, as I've suggested before, in a number of different ways. The first sentence can also be written in the style, and now this is the style of the deterministic finite automata. So although the language is logical English, the language can simulate deontic modal logic, or the language can simulate deterministic finite automata. So the language, like ordinary English, allows many different styles of representation, many different styles of expression. So the second representation is in the style of finite deterministic automata. The lender becomes liable to litigation, which is implicit in the obligation for the lender to advance the funds if it is the end of 2014, the 2nd of June, and the borrower has requested $1,000, and it is not the case that the lender has advanced the loan. So the obligation gets twisted. It only gets represented in terms of what happens if the obligation is breached. So the first sentence represents the obligation straightforwardly, and it doesn't draw any conclusions about what happens should there be a breach. Whereas the second representation builds into the representation that failure to advance the loan constitutes a breach, but not saying that explicitly, rather saying, in fact, that if it should occur that the lender does not advance the loan, then the lender is liable to litigation. This is a way of treating deontic concepts and obligations implicitly rather than explicitly. And the co-author, Oliver Goodenough, has written extensively against deontic logic, saying that we can avoid deontic logic and avoid talking about obligations by talking instead about state transitions. Now, I'm not going to argue with that, because in fact, when I read the paper, I was quite convinced that that ontology, that way of thinking about things, was actually quite useful. And I implemented their loan agreement in a lower level, prologue-like language, using this way of avoiding explicit obligations. Look instead now at the second sentence. If the borrower does not make such a request, this agreement will terminate. No obligation here. The contract will become terminated at a time if it is the end of the 1st of June, 2014, at the time, and it is not the case that the borrower has requested the loan at the time. Now, you may not like this, and I can see why from the looks on your faces. You don't like this explicit representation, a time, the time. In ordinary language, we don't talk this way. We don't speak this way. And that's because we have easier, simpler ways of talking about time. We could instead say the contract becomes terminated when it is the end of the 1st of June 2014, and it is not the case that the borrower has requested the loan. Now, the question is this precise? Is this logical? Is this as rigorous as the sentence I first showed you? And the answer to that question is yes. And there is a transformation in the sense of Chomsky's transformational grammars that allows you to take a sentence of the form, some conclusion holds when some conditions hold, and translate that into a more precise statement about a conclusion holding at a time if the conditions hold at the same time. So we can imagine the hierarchy of logical English statements. The lower representations are closer to the implementation, in a sense closer to the actual meaning, whereas the higher level representation, this one up here, is closer to ordinary English. So you start with ordinary English, remove passive, translate passives into active voice, as in Chomsky's grammars, remove the word when by introducing explicit references to time, and we can go further and take this one or several levels deeper and translating it into symbolic, logical, executable notation. The notation you see here is a higher level than prologue called logical production system, which involves sentences of this logic programming conclusion if conditions form, but also other kinds of sentences I'm going to show you in my next example from the cryptocurrency field. So this particular example has been implemented in LPS, logical production system language. It runs online, and this is an extract from that program. It's an extract that doesn't use explicit time already. And I can give it a sequence of imaginary external observations about the borrower requesting the loan at 3 o'clock on the 1st of June, 2014, the lender advancing the loan at 6 p.m. on the 2nd of June, the borrower paying the lender back $550, that's to say half of the loan plus 5% interest 1 year later, and then finishing by paying another 5% and the principal another year later. And we can automatically generate the state transition graph from the logic in this particular implementation. So I'm not arguing by any means that definite deterministic finite automata are not a good way of thinking or visualizing state transitions in the real or imaginary world, but rather there's no need to get rid of English or natural language, and in particular no need to get rid of logic in particular. I have 2 more examples. I think I would probably skip this example because I want to spend more time on the last example, but I'll flash through it. Close your eyes if it's too blinding in the process. So there is this widely cited paper, 259 citations for a paper written in 2016 is quite a large number. And they talk about the rock, paper, scissors game. I've been told everybody knows this game, although I didn't at the time. And here is an attempt in our Swish implementation, an early version of logical English, which represents the game. And here is the underlying prologue-like implementation. But I want to draw your attention to these 2 sentences here, which describe the game. In particular, if I look at this rule is not a logic programming prologue-like rule. It's a rule that has an imperative interpretation. So logical English is intended to close the gap between declarative and imperative sentences, and it's intended to have the same expressive power as imperative programming languages. So in symbolic notation, and if you read this imperatively, the sentence says that if a player has played a choice, rock, paper, or scissors, and another player has played another choice, rock, paper, scissors, and the choice, namely the first one, beats the other choice, namely the second one, and the game is not over yet, and the reward is a prize, then end the game and pay the player the prize. You have to end the game because you don't want 3 people playing at once, and that's why one of the conditions is that the game is not over, and one of the conclusions is that make the game over so that you lock the system so that you don't get the problems that were identified in the cryptocurrency world. So now why is this using imperative language? It's using imperative language because the computer is being used as an agent. The computer is not only passively judging states of affairs, but it's actively involved. It is stopping the game to prevent interference between too many players, and it's also paying out, transferring funds from one player, from the system itself to the other player. But this can also be stated declaratively. Instead of stating the conclusion, then end the game and pay the player, it can be stated as in a purely declarative, legal-like manner by saying then the game becomes over, the game is finished, and the player is paid the prize. So what does this mean? Well, go back to 1958, to the philosopher Peter Geach. The logic of imperatives, he says, is, I think, fairly trivial, and I would agree with him. For every proper imperative, and for every imperative programming language, there is a future tense statement whose coming true is identical with the fulfillment of the imperative. This is the source of everything that can be said about the inferability and compatibility of imperatives. There being imperatives does not affect these logical interrelations. That was stated, how many years? 60 years or so ago, and there's still some merit in reading old papers. Well, I want to now look at my last example. And as I said, I had a master's degree student working on this over the summer. So this is the International Swaps and Derivatives Association Master Agreement. Stefan knows far more about it than I do, but I've been looking at the logic and at the English, and I've been having problems. So first of all, the Master Agreement is meant to be a standard agreement which is not altered. Every over-the-counter trade is supposed to conform to the Master Agreement. However, you can override certain clauses by a schedule, and then you have various confirmations that involve individual transactions. This is my master's degree student who just finished and who is working for the Bank of England. I'm hoping that he'll come back to this application in the near future. Well, here's a very simple, I'll start simply. Each party, there are two parties, the party and the counterparty, will make each payment or delivery specified in each confirmation to be made by it subject to the other provisions of this agreement. Notice will. This is an obligation. Each is like all or some, so we have to replace that by a. So it is an obligation that a party performs an action if the action is specified in a confirmation and the action is a payment or the action is a delivery. So this is quite simple, you might say, so far. Quite simple, quite straightforward. And notice that the indefinite article or an and the definite article the allow us to avoid all, some, each, and every, all of those sentences in English which have a logical interpretation. But what about this subject to the other provisions of this agreement? What does that mean? Well, the other provisions are the ones, for example, in the schedule and elsewhere in the master agreement. And what they do is they allow the conclusion not to hold if certain conditions hold. In particular, the conclusion will hold if it cannot be shown that it is not the case that the obligation holds. So this is like saying a bird can fly if it is not the case that the bird cannot fly. So you have maybe an argument that says the bird can fly. You have another argument that says the bird cannot fly, but the second argument trumps the first. So from an argumentation theoretic perspective, we can view this as one argument rebutting the other. We can say, what does it mean for an obligation to be satisfied? Which is why it's better to represent this as saying it is an obligation, just like saying it is a bird. So by we call this reification and nominalization. By reifying obligations and making them individuals, we can talk about them and talk about whether they're satisfied, an obligation is satisfied. If the obligation is that the party performs an action, this is not only reification, but it's either higher order logic, second order logic, or meta logic, depending on your point of view, and the party performs the action. And an obligation is violated or breached if it is not the case that the obligation is satisfied. These act like the axioms of a modal deontic logic, but they're executable in prologue. So you need to have ways of reasoning and thinking about obligations, but you don't need to go to the complexities of deontic logic to do so. Well, this is the interesting clause I want to draw your attention to, netting of payments. If on any date, amounts that would otherwise be payable in the same currency, pounds, euros, what have you, and in respect of the same transaction. So there's one transaction, but there might be certain amounts, payments, all due on the same day in the same currency by each party to the other. Again, the each and the other. Then on that date, so you're talking about fixing a date, fixing a currency, and fixing a transaction. On that date, each party's obligation to make the payment will be automatically satisfied and discharged, and if the aggregate amount which would otherwise have been payable by one party exceeds the aggregate amount that would otherwise have been payable by the other party, replaced. Will be replaced. So the original obligation, each party's obligation will be replaced by an obligation upon the party by which the larger aggregate amount would have been payable to pay to the other party the excess of the larger aggregate amount over the smaller aggregate amount. Now, so I'm not complaining about the complexity of the English. I'm complaining about the complexity of the logic, and in fact, that the logic is incorrect. The logic does not say what most people read it as saying. Most people, if you search the internet for netting of payments, interpret this incorrectly to mean it is optional whether or not you net payments. But here it clearly says it's not optional. You're under an obligation. Anyway, that obligation becomes far clearer both to humans and machines if we rewrite this in the logical English I've been describing. So, this is an exception to the obligation rule. It is not the case. So remember the previous sentence says that it is an obligation for each party to make the payment specified in each confirmation. But this earlier obligation replaces the old obligation and therefore prevents the old obligation from being applied. It is not the case that it is an obligation that a party pays to a counterparty an amount in a currency for a transaction if it is obligatory that the party pays a net amount. So here I'm distinguishing between a bird and a flying bird. So we have we have a variable, a logical variable of type amount, and we have another logical variable of type net amount. These are different types. So if there's an obligation to pay a net amount, then this cancels the obligation to pay the ordinary amount. And there is an obligation to pay a net amount if the net amount is a larger aggregate amount minus a smaller aggregate amount. The larger aggregate amount is the sum of each amount of each payment. Now here I have used the word each. I've needed, I can't just say because there would be an ambiguity. Of each amount of each payment by the party to the counterparty in the currency for the transaction on the date, and the smaller amount is the sum of the amount of each payment by the counterparty to the party in the currency for the transaction on the date. For those of you who know Prolog, this sum of translates directly into one of Prolog's aggregate operators, so it translates quite simply into Prolog. And I claim that this is executable by machine, more easily read and understood and more correctly read than the original English. So logical English is not only English, but it's possibly easier to understand than ordinary English. Well, I wrote a paper more than 25 years ago where I argued, like I argue today, that the linguistic style in which legislation is normally written has many similarities with the language of logic programming, and this was picked up by the British press. And the good news is that programmers will someday go away and be replaced by lawyers, so there's going to be plenty of opportunities for the legal profession. And if you want more information and more opinionation, you can go to my webpage, you can look at my book, you can look at the language LPS, the startup company, Logical Contracts, and my master's degree student, and I want to thank my colleagues. And I want to thank you.
Robert made very clear is, why does a lawyer need to understand the logic and the language of its language in order to get to an executable version. And the other way around, if somebody does provide a computable program on legal language, why do you need to understand how that works? Because otherwise you won't be able to follow what's happening.